Many outcomes of interest in economics are binary. For example, suppose that y equals 1 if a person is employed and 0 otherwise. We might want to try to predict y using a collection of regressors x that include age, sex, education, experience, and so on. The question we might ask ourselves in this situation is, how does a particular one of these regressors, call it xj, affect our prediction of y if we hold the other regressors constant? We'll consider three popular models for binary outcomes in this lecture. The first is called the linear probability model. The second is called logistic regression, or logit. And the third is called probit regression, or probit. Models for binary outcomes have some special properties, and on this slide we will review the most important ones. Throughout this lecture, I'll use the notation p of x to represent the probability that y equals 1 conditional on x. The two key properties of binary outcomes that we'll use in this lecture are as follows. First, the conditional mean of y given x is equal to the probability that y equals 1 given x if y is a binary outcome. And second, the conditional variance of y given x is equal to p of x times 1 minus p of x if y is binary. Let's prove these two results. We'll start with the first one. By definition, the conditional expectation of y given x is equal to the sum of the products of each possible realization of y multiplied by the probability of that realization. Everything here, of course, is conditional on x because we're evaluating a conditional expectation. Because y can only take on one of two values, 0 or 1, we obtain 0 times the probability that y is 0 given x, plus 1 times the probability that y is 1 given x. Of course, that first term is 0, so we're left with the probability that y equals 1 given x, which I have defined to be p of x. To calculate the conditional variance, we will use a well-known result about variances, namely that a variance is equal to the difference of the expectation of the random variable squared minus the expected value of the random variable quantity squared. Since we've already calculated the conditional expectation of y given x, all that remains for us to calculate is the conditional expectation of y squared given x in order for us to calculate the conditional variance. Again, using the definition of an expectation for a discrete random variable, we have the expression 0 squared, that is to say the realization squared, multiplied by its probability, 1 minus p of x, plus 1 squared, the other possible realization squared, multiplied by its probability. And once again, we find the result is p of x. Substituting this into our expression for the conditional variance, we find that the conditional variance of y given x is equal to, as asserted, p of x times 1 minus p of x. The first model that we'll consider for a binary outcome is called the linear probability model. This model assumes that p of x is equal to x prime beta, where beta is an unknown vector of parameters. This is really just a linear regression model. The linear probability model is a fancy way of saying if you've got a binary outcome, just ignore it and run linear regression. So let's work out some of the properties of this model. Using the result from the previous slide, we know the conditional mean of y given x in a binary outcome model is equal to p of x. Thus, in the linear probability model, this conditional mean is equal to x prime beta. Similarly, using our result for the conditional variance, we find that in the linear probability model, by substituting x prime beta for p of x, the variance of y given x is x prime beta times the quantity 1 minus x prime beta. So why is it that this is just the same thing as linear regression? Well, it's because we can in fact write y as the sum of two components. First, x prime beta, and second, u, an error term, where we construct this u such that the expected value of u given x is 0. In other words, we can write y in the form of a linear regression model. So why is this the case? Well, we'll use the assumption that p of x equals x prime beta, and let's define u to be the difference y minus x prime beta. What is the conditional mean of u given x? Well, substituting the definition of u, we see that the expected value of u given x is equal to the expected value of y given x minus x prime beta. Here we've used the linearity of conditional expectation. We've also used the fact that x prime beta is a known constant once we condition on x. Anything minus itself is 0, so we have shown that the expected value of u given x is indeed 0, which justifies my claim from before that the linear probability model is just ordinary least squares regression. There's one important wrinkle, however. The error term u, as we have just constructed it, namely the difference between y and x prime beta, is necessarily heteroscedastic. In fact, the variance of u conditional on x is equal to x prime beta multiplied by the quantity 1 minus x prime beta. To show this, we will use the definition of conditional variance to write variance of u given x is equal to the expectation of the following object, u minus its conditional mean given x, whole thing squared, conditional on x. But as we've just seen, the conditional mean of u given x is equal to 0. So this expression reduces to the expected value of u squared given x. Now, substituting the definition of u, namely u equals y minus x prime beta, and using the linearity of conditional expectation after expanding this quadratic, we obtain the following expression. The first term is the expected value of y squared given x. Then we have a minus 2 times the expected value of y given x multiplied by x prime beta, where again here we have pulled out the x prime beta from the expectation because this is just a constant once we've conditioned on x. And the final term is x prime beta squared. Once again, this is not within an expectation because this is just a constant conditional on x. Recall from the previous slide that we calculated the expected value of y squared given x is equal to p of x, and moreover, that the expected value of y given x is equal to p of x itself. And indeed, because the linear probability model assumes that p of x is x prime beta, we see that the variance of u given x is equal to p of x minus 2 p of x times p of x plus p of x squared. Simplifying this expression, we obtain p of x times 1 minus p of x as asserted. Because the linear probability model assumes that p of x is equal to x prime beta, we can just run OLS, and because we've shown that the expected value of u given x is 0 under this assumption, this OLS estimation of the model y equals x prime beta plus u will provide an unbiased and consistent estimator of beta. We just have to be aware of the fact that because u is a heteroscedastic error term, any tests we might wish to conduct and any confidence intervals we may wish to construct should use robust standard errors. So that's what the linear probability model gives us. The question remains, is it actually reasonable? Notice that the linear probability model assumes that p of x, namely the probability that y equals 1 given x, is a linear function, namely x prime beta. This implies that if we were to change one of the regressors, xj, by an amount delta, this would change our probability for y being 1 given x by an amount beta j times delta. But notice that this implies that if our vector of regressors x contains any predictor without an upper or lower bound, then p of x could be greater than 1 or less than 0. That's not so great for a probability. This shows us that the linear probability model, while it might be a reasonable approximation over a certain range of values for x, cannot be literally true. There is an important exception to this claim, and you will work that one out on the problem set. Because the linear probability model has this limitation, we now have a motivation for considering models that do not yield probabilities outside of the range 0 to 1. We'll take a closer look at these in the following videos.